Hello class, this is the video for section 3.10. Talks about linear approximations and differentials. The following our learning objectives, the students will be able to use linear approximations to simplify a function and use differentials to estimate errors that occur because of approximate measurement in sciences and engineering. Okay, so we first want to look at the linear approximation. Okay, so we have seen that a curve lies very close to its tangent line, near the point of tangency. Okay, that is the point of contact. In fact, if we zoom in toward that point on the graph of a differentiable function, we notice that the graph looks more and more like what this is tangent line. And so basically the linear approximation that we're going to talk about is the equation of the tangent line. Okay, so the idea is that it might be easy to calculate a value f at a certain point of a function, but difficult or even impossible to compute the nearby values of the function. Okay, so this is what happens. This is the graph. So we have this curve which is differentiable f of x, y is equal to f of x, and we pick a point on it with the x coordinate a and the y coordinate is what f of a. So you have x, this is a, and then this is what? That is what f of a, like that. So if you look at this point, the graph of the function or the curve is approximated to what? The linear function, which is the equation of the tangent line. And this is what we will call the linearization. In fact, we are trying to say that in this world, everything is linear because we can use that linear approximation to any curve at all. Once we pick a point, and if you want to find the rate at which that curve is changing, is what rising, or the slope of the curve is what going up or down, it has to be the approximated to the linear function, which is the equation of the tangent line. Okay, so this is what is happening. So if you have that point with the coordinates f of a, right, on the curve, and then you know that this is you know that the slope is what? F prime of what? F prime at the point, okay? And this is the y coordinate of the point. So the equation of the tangent line basically is given by what? This equation right here. Y is equal to f of a, which is supposed to be y minus f of what? A equal to the slope at a and the x minus a. And then when you add this to both sides, you get that equation. So the whole function f of x at this point with the coordinates a at the point x equal to a, that function f of x is what? Approximately equal to this line. And so we're going to replace this f of x and use what? A different function, which we call L of x, which will be the linear approximation to that. So the whole of this is called what? The linear approximation, or the tangent line approximation of what? F at what? At a. Okay, so this gives us this equation we call the linearization, because we approximate the linear function to the whole curve at the value x equal to what? A. And this is what we call the what? The linear function. So when I ask you to find the linearization, approximate the linear function, this is basically the what? The slope. So the equation of what? The tangent line. Okay, equation of the tangent line, simply put. All right, so here's example. So find the linearization of the function f of x equal to square root of x plus 3 at a equal to 1. Now, we're going to use that linearization to estimate the value of what? The square root of 3.98 and then square root of 4.05, which we are approximating that value because we can use a calculator to evaluate this. So let's see how this turned out to be. Well, this is my function f of x because the square root of that. Now, if you look at the equation, the linear function is what? is f of a plus the slope, which is what? The f prime at a times x minus a. All right. So if I have f of x, I need to first what? Define the function, differentiate the function, I mean, and then evaluate it at what? X equal to a. And so if we differentiate this function using the chain rule, you're going to have 1/2 x plus 3 raised to what? Negative 1/2. And then the negative value comes down, so you get this function. So the question is that since my a is equal to 1, my linearization is what? It will be f of 1 plus f prime at 1 times x minus what? X minus a. So we need to find what is f of 1. Okay, if you plug 1 into the function, all right, see that you have what is f of 1. I have it here as 2, so this was square root of what? 1 plus 3, which is square root of 4, and that is what? 2. That's why we got a 2. So then we also have to find the f prime at what? At 1. Okay, which is equal to 1 over 2 times the square root of what? 1 plus what? 1 plus 3. Now this would give me 1/2 times 1/2 over, sorry, of 2 times 2, which is what? The 1/4. That is why we have the 1/4 here. So then we can write down our linear what? Linear function, okay, which is what? L of x will be equal to, as you can see, what is my f of a? You have what? 2 plus the slope is what? 1/4 the x minus 1. Now let's simplify that. This will be 2 minus 1/4, okay, plus 1/4 times x, which will give us 7/4 plus x over what? Over 4. And so the linear function is equal to what? Is equal to that. So what we are saying is that, okay, the f of x is approximately equal to what? Okay, which is equal to the what? 7/4 plus x over what? Over 4. So what we are saying is that the whole function, the x plus 3, is actually approximated to the L of x, which is equal to this function right there, plus x over 4. Okay, so then it says that we should use this linearization to approximate this value, the square root of 3, okay, the square root of 3.98. Now, 3.98 can be written as what? Because it's x plus what? We want to know what the x is, and then before we can what? Approximate that, right? So first, what we have is that this is the same as what do you call it? 0.98 plus what? Plus 3. So that implies, if I compare this to what we have there, okay, if you compare this to the square root of what? X plus 3, it means that x is equal to what? 0.98. Okay, so therefore, to approximate this number, okay, this means that the square root of 3.98, okay, is approximately equal to 7 over what? Over 4, then plus x is 0.98 divided by what? Divided by 4. Now, when you evaluate this, this is equal to 1.995. Okay, 1.995. All right. Now, the other value is that I say use it to evaluate 4.005. Now, remember this is still equal to what? X plus what? 3. So we need to figure out what the x for this value. Well, as you can see, the 4.05 is the same as what? 1.05 plus what? Plus 3. Now, if you compare them, it means that your x will be equal to 1.005. So we use the same approach, okay, to evaluate that. Therefore, the square root of 4.05 is approximately equal to what? 7/4 plus x, which is 1.05 over 4. So if you evaluate this, you get 2.0125. Okay, so our approximation what? Basically, if you take this value, you're going to see that the approximation what will overestimate, because the tangent line lies what above the curve. Okay, now all these estimates, these over what? This what? These overestimates estimates what? The values. Okay, estimates, overestimates, because the tangent line lies what? Above the curve. Okay, so the tangent line, what we mean is what? The L of x, basically, okay, what lies above the curve, which is the f of x in this case. So that in the graph, this is what is happening. Okay, this is my, don't forget, this is my L of what? That's my linearization, which is the equation of the tangent. It lies above. That is why it is what overestimates the square root of 3.98 and then square root of 4.05. Okay, so let's find other examples. Exercise number 1 says find the linearization L of x when you are given this function at a equal to -2. All right, so what we do is that, don't forget the L of x, the linearization, is given by f of what? A plus the f prime at a times x minus what? A. So what we have here is that our a is equal to -2. Our f of x is given us, as in the question, is what? X cubed minus x squared plus what? 3, and a is equal to that. So let us find first what is f of what? -2. This will give us -2 cubed minus -2 squared plus what? Plus 3. Okay. And when we do that, that is equal to -9. Okay. We simplify that, get -9. So then to find f prime at a, we need to differentiate it first. So let's differentiate f of x, which will give us 3x squared minus 2x. All right. Then we need to find f prime at a, which is the a is -2. So let's evaluate that. This will be 3 -2 squared minus 2 times -2. And then when you evaluate that also, you get 16. Okay, you get 16. So therefore, my L of x is equal to f of a. Okay, so that would be f of what? -2 plus f prime at what? -2 times x minus -2. So that would be plus what? Plus 2. All right. So then this is, we found this word -9, then plus what? 16. Okay, times x plus what? 2. Now when we simplify this, we get -9 plus 32, and then that is plus what? 16 what? X. So the linearization L of x is equal to what? 16 what? X plus 23. That is my linearization for this what? For this function at x equal to -2. Okay. Now here is another example that we have f of x is a sine of x, and then a is pi by 6. All right. So like we said, the linearization formula is what? F of a plus f prime at a, then x minus what? Times x minus a. Okay. So first we need to find what? F at what? Pi by 6. That is my f of a. This is your f of a. Okay. Now, what is that? This is what? Sine pi by 6. Okay. Now, what is sine pi by 6? Okay. Sine pi by 6 is basically what? Sine of, that's pi by 6 is what? 30 degrees. So that's what? 1/2. Okay. So now let's find f prime of x, which is what? Cosine of x. Okay. So then let's find f prime at what? Pi by what? 6. So what is cosine of what? Pi by 6. Okay. Now cosine of pi by 6 is what? Square root of 3 over what? Over 2. Therefore, the linearization L of x is f prime. So f of pi by 6 plus f prime at pi by 6. Then times x minus pi by what? By 6. All right. So then, if you substitute these values, you have what? It will be 1/2, okay, plus square root of 3 over 2 times x minus pi by 6. Okay, we'll leave it at this point. Okay, we can simplify it, but that's okay. Let's leave it at this point. So that's my linearization. For this function. All right. Now we go to the second phase, find differentials. Now differentials is what? Okay, don't forget we are looking at dy dx for y is equal to f of x as a differentiable function. Dy dx is equal to what? F prime of x. So if we solve for dy dx, which is basically f prime of x times what? Dx. So this is what we're going to call the differential. All right. Now, don't forget that the ds is just a small change in x. Okay. That's why we can find a what? If you remember, when we were finding the slope of the tangent, we had a point P and a Q, and then we vary the point Q and move it as it's getting closer and closer to P. Okay. We have a tangent line. So that's the limit. Concept right there. Now, in this case, what we do is that the idea behind linear approximations are sometimes formulated in a terminology and notation of what we call differential, as I've just gave you a glimpse of. Okay, if y is a function of x, okay, and it is differentiable, then the differential d of x is an independent variable. So that's going to change. That is for a small change in x, okay? So ds can be given the value of any real number. So if it's independent variable, then it becomes what? Independent number. It's a real number, that could be anything. Therefore, the differential, which we'll call what? dy, sorry, is given by this formula that I wrote it down in the previous slide. Okay, so what is happening is this. Here is a curve. That's my f of x. The blue is my f of x. And then we pick a point P and then Q. Okay, so we draw a tangent to the curve at P. And then we pick a point R on the what? On the line, the tangent line, which we call, in this case, would be the L, the linearization. So the coordinates of the P are what? X, okay, because it's on the curve. This is what? F of what? X. And then Q is here. K has what? The small increase in what? X. That's a change in what? Change in the X values will be X plus delta of what? Delta of X. And then that gives me the coordinates of what? The Q, the point Q on the curve. Okay. The dy, which we are calling the differential, okay, which we are calling the differential, okay, what is it? Remember what your discussion to this week, you have to know what that is, okay? This is just now as you move this point P on the curve, along the curve, you can see that the slope is either going to rise or fall. In the other words, be higher in value or decrease depending on if you are moving it to the right or to the left. Okay, the steepness of what of the tangent line. So basically, this is what it just telling me the amount of what the rise and fall of the tangent line. Okay, now if we still have this point Q on that, the delta, this is the change in y, small change in y over change in x, which we used to find the what the slope. Remember, the slope m was what delta y over what delta what x. That time we call it change in y over change in what change in x. Now, if that's the case, then that is given by the difference between the function value, okay, the y coordinate at the point Q, and the y coordinate at the point what f, sorry p. So it's a difference between the y coordinates. So this is basically what the difference between the what the y coordinates. Now that represents the amount of rise and fall of the what of the curve for a small change in what small change in x. Now in terms of notation, as s gets smaller and smaller, okay, the delta y will approximate what dy dx, and then the delta x will approximate what dx. Okay, so we need to find a differential using the formulas that we just talked about. Now here is an example. Our first example is that we want to compare the what the delta y and then the differential dy for a function f of x, x cubed plus x squared minus 2x plus 1. And we want to use that a for small changes in x from 2 to 2.05 and then 2 to 2.01. So we want to see what we'll use this, this for. Okay, now we are given a, we want to find a, we know that x is from what? We know that x is what? From 2 to what x equal to 2.05. Okay, so in this case, what is the small change in x? Is a difference between the two. So 2.05 minus 2 will give me 0.05. So that's that small change in what? Small change in x. All right. So what is this value? This is given by f of what? X plus a small change in x minus f of what? F of x. Okay. So x is what? 2. So you see that this is the same as what? F of what? 2 plus 0.5. That gives me what? 2.25 minus f of what? F of 2. Okay. So what we do is that we go to the function and plug in these values. We want to find f of 2.05, which is what? 2.05 cubed plus 2.05 squared minus 2 times 2.05, then plus 1. Now, if we evaluate this carefully, you have what? 9.717625 to 6 decimal places, and also find f of what? 2, which will give us just 9. Okay, so if you find the difference between them, what is this value? What is that? That value is the difference between them, which is 9.717625 minus 9, which will give us 7176225. Okay, so we want to compare this to the dy, the differential, which is what? F prime at what? X times what? Dx. So the question is that what is dx? Okay, the dx will be the same. Don't forget that the dx is equal to this value, which we just found, which is 0.005. Okay, so we want to differentiate the function. F prime of x is what? 3x squared plus 2x minus 2. Okay, but x is equal to 2 because don't forget it's from x equal to 2 to the small increase, which is 0.05. So then let us find f prime at what? At 2. Okay, f prime at 2 will give us, which will be 3, 2 squared plus 2 times 2 minus what? Minus 2. Okay, that will give us 4. This is 12 plus 4 minus 2. That is what? This will give me 14. Right? Because you get 12 minus 2 is 10, that's 14. So then the dy dx is what? The f prime, that is 14 times 0.05, which is basically equal to what? 0.7. Okay, so this is the difference. This is the delta y. The value is 0.717625. And then the dy, the differential, okay, this is the what? The differential. That's the differential is what? 0.7. Okay. Now part B, we want to also do the same thing, this time from 2 to what? 2.01. Okay. So part B, okay, B is here. Okay. I'm going to write that B here. So again, we do the same thing as we did before. Okay. Now delta of y is what? F at x plus delta of x minus f of x. Now x is still 2. Now delta of what? X is actually the 2.01 minus 2, which will give us 0.01. Okay. So we do the same thing as we did before. We know that, of course, f of 2 is 9 as calculated before. So what is f of 2.01? Okay, that will give us 2.01 cube, okay, plus 2.01 squared minus 2.01 plus 1. Okay, so when we evaluate that also, we get 9.140701 to 6 decimal places. So therefore, what is this delta? Okay, that's a small change in what? Y. It's going to be 9.140701 minus 9, which is equal to 0.140701. Okay, so then let's find the differential. Dy is what? F prime of x dx. Okay. Now, f prime of x dx. This, we know the f prime what it is. Okay, f prime is still the same, doesn't change. It'll be 3x squared plus 2x minus 2. So then we evaluate this at what? X, okay, which we calculate this is what? This is 14. Okay, so I have 14 times what? So therefore the dy is what? 14 times 0.01. Okay, because now one thing you should notice that the dx is equal to delta x, and then from up here, this is what? 0.01, not 5. Now when you can multiply this, you have what? 0.14. Okay, 0.14. All right. So we want to note that it's a very important thing to do. All right. So that is that example. Now I was going to do B here, but I've already done it. Now we want to continue this, solve these two examples whereby we want to find the differentials of each of them. Now here, what's our differential is what? The dy, this one. This is my differential. That's what we are looking for. Now dy is what? F prime of x times dx. Okay. We don't know if you are given the dx, which will be a small change, all right? If you're given the dx, you can always evaluate what? The differential. So let's differentiate this. Okay, what is f? This is my f of x is what? X e to the minus what? 4x. All right, so then let's just differentiate that. What is f prime of x? Okay, so keep the x, differentiate that. You have what? Minus 4. Okay, to differentiate, sorry, yeah, you have e, let's go this way. This is x times e raised to a minus 4x, then times what? Negative 4. Okay, then plus, now you keep e to the what? Minus 4, then differentiate the x, which is 1. So this is equal to negative 4x e raised to minus 4x plus e raised to minus what? 4x. Okay, so then the dy dx, so just dy, the differential, dy is given by that whole thing, okay, which we can write as e raised to the minus 4x, okay, minus the 4x e raised to minus 4x. Now all this times what? Times dx. Okay, similarly, your f of x, in this case is f of t, is equal to the square root of what? 1 minus t raised to 4. Okay, so f of t is 1 minus t raised to 4 all raised to what? 1/2. So first, let's differentiate that. Okay, let's differentiate f of t, which is what? 1/2. 1 minus t raised to what? 4 raised to 1/2 minus 1, which is minus 1/2. Chain rule, and that is equal to minus 4t raised to what? 3, like that. So this is actually equal to negative, well, the 2 goes into 4, which is what? 2. So we have minus 2t to the 3rd power divided by 1 minus t to the 4th power raised to what? 1/2. Or you can just write this is the same as minus t, negative 2t to the 3rd power divided by the square root of what? 1 minus t to the 4th. So then the differential, okay, the differential, okay, dy is what? F prime of x, sorry, t, times what? This will be dt, not dx. Okay, so then let's substitute that. This will be what? Minus 2t cubed over the square root of what? 1 minus t to the 4th, then dt. Okay, so that will be your answer for that. Good. So we use this to estimate the differentials to, that's the second objective, to estimate the, what we call the errors, okay? And so we're gonna use that for this problem. Okay. So here's the question that if we have, say, a radius of a circular disc, okay, is giving us what? 24 centimeters when the maximum error in measurement of what? 0.2 centimeters. Measurement in error. Okay. So use differentials to estimate the maximum error in the calculated area of the what? Of the disc. Okay. So we know that it is a what? It says it's a circular disc. So the area, okay, A for a circular disc is given by what? A circle, so pi r what? Pi r squared. So according to this, what is the radius? Radius is given as what? 24 centimeters. What does this? What is this? Okay, that is the what? That's your dx. Okay, because the dx in this case, because it's in terms of what? Area is in terms of the radius, that will be your dr. That's a small change in what? Small change in, so that's your dr is what? 0.2 centimeters. Now, by the what? Okay, by the differential, remember it is what? Dy is equal to f prime of x dx. Now, this is the y is your area in this case. So it's going to be what? dA is equal to what? The a prime at what? At r times what? dr. Okay, so let's differentiate this. What is a prime? It's going to be what? 2 pi what? 2 pi r. Okay, 2 pi r times what? Okay, 2 pi, that's a 2 pi r. Okay, it's just that. Well, so therefore my dA is what? 2 pi r dr. Okay, and then when we substitute this, we can be able to what? Evaluate that. So we have what? 2 pi, r is what? 24, and then dr is what? 0.2. Okay, now if we evaluate everything, you have what? 9.6 what? 9.6 pi. Okay, this is what we call, this is the maximum possible error in the calculated area of the disk. So this is what we have there is what? The maximum, okay, the maximum error as we calculated is a maximum what? Maximum error in calculating what? The area of the disk. So if I'm manufacturing this disk, okay, I can use differential to estimate the, if there's any error, which is always there, that could be the maximum area or maximum error in calculating the area. Okay, when you are given this what? 0.2 centimeters what? In error of what? The radius of the disk. Okay, so the second part says that what is a related what? Error. Now, and then what is a percentage error? Okay, now related error is, let's start with that one. Related what? Error. Okay, this is associated with what? The error in measuring what? The area with respect to what? The area, which is what we call it. This would be what? This is the change in A over A, and that's approximately equal to what? dA over what? Over A. So what we have there is that we know dA is what? 2 pi r dr, and then the area is what? Pi r squared. So when we simplify this is basically what? This will be 2. This will be 2 dr over what? Over r. Okay. So let's evaluate that. This is equal to, let's write it down here. This will be 2 times dr, which is 0.2, over r, which is what? 24. And this is equal to what? 0.01667. Maybe 0.1666666. Okay, so therefore, what is the percentage what? Error? What's the percentage what? Error? Okay, now percentage error is equal to the relative error times 100%. That's the definition. The relative, did I say related here? This is supposed to be relative. Sorry, it's what? Relative, not related. Relative error times 100%. So what we got there 0.0166667 times 100%. That will give us 1.6667. Okay, 667%. So that is your percentage error. That is your relative for L. So that brings us to the end of this this video. Thank you.